second. Isn't that interesting? That's how fast the car was going this way before. Isn't that interesting? Now, let me explain what's going on here. It's actually a really cool idea. The time it takes for this to fall 5 meters if you launch it horizontally at 25 meters per second is the same time as if you drop it. In fact, I'll go a step further. If you would launch it at 8,000 meters per second and there was no air resistance, and you launch it horizontally, the time it would take you to fall 5 meters would be exactly 1 second. In other words, it's the same. The time to fall has nothing to do with how fast you launch it horizontally. That's sort of our big idea here. Now, if you think about this logically, I'm going a little deeper than I went in my last class. I probably should have talked about this, but I had this sort of analogy. So let's say you try an experiment like this, even simple, you just drop something. But you're on an airplane that's cruising along at constant speed. Would you expect when you drop it, it'll fall just like it does in here? But to someone down on the ground watching it, it's moving along with the plane as it falls. In other words, if you see it fall straight down and land right at your feet, but you're moving in the plane, then it actually did not do that. See how that works? According to someone on the ground, at least, it wasn't going straight down. It was going like this. See? Yet you would expect to time it just the same. Right? Of course, if they were timing it, it'd be a very different scenario where you were getting the same time. So the point here is this horizontal launch speed has nothing to do with the time here. And I can actually demonstrate this. So let me show you this cool little gadget. So this little object here, a little marble, and this marble are more or less the same. This one has a little hole in it, so I can just place it here. And the idea is, I can push, there's a spring here that I cocked the spring. I can push this way, and this one is going to go flying off that direction horizontally. And this one's just going to fall. And in theory, if this one's launched horizontally from the same height that this one's dropped from, they should hit exactly the same time. Does that make sense? If this works perfectly anyway. So let's try it. Ready? Set. You can almost just hear it. Can you hear them hit simultaneously? Okay. Isn't that cool? Isn't that cool? And it doesn't matter how fast you launch the thing horizontally. At least not if we're ignoring air resistance. It makes no difference at all. Now, all of this will make a lot more sense in terms of the why this is true once we get down the road into forces. It'll turn out the explanation for this is going to be tied to the fact that gravity acts down. Gravity is the only force acting, and if it's acting down, it can only affect motion vertically, so it can't have any effect on what's going on horizontally. That's what's really happening here. But for now, just accept with me, having seen it empirically, right, I've seen experimentally, that this is the case, right, that the vertical motion is the same. Okay? Now, let me show you what's going on as a picture. I'll draw you a picture of what's happening. So imagine you take an object, you launch it horizontally. Here's what it would look like. Let me erase this. Okay. So let's say I draw this picture, and I take this object, and here it is, and you launch it this way. And you launch it at some speed, some speed v, horizontally. Now, imagine that I took another object and I just dropped it. And the object that I dropped is going to fall, right? In 1 second it falls a certain distance, in 2 seconds it falls farther, in 3 seconds it falls further. You get the idea because it goes faster and faster. In fact, hopefully we're good with the idea. The distance it falls is just 1/2 gt squared. This is the displacement equation with v initial is 0, basically, where I call down the way it's moving. So it goes as time squared. However far it goes in the first second, it goes 4 times as far in the first 2 seconds combined. Because it goes as t squared. Double the time, you go 4 times as far. Triple the time, you go 9 times as far. So it goes further and further and further. So in theory, let's say in 1 second, this is time equals 0, it falls from there to there, then it should in theory fall 3 times as far, so a total of 4. So 1, 2, 3, 4. So that's about right. To about here at time equals 2 seconds. So here's time equals 1. And then by time equals 3, it's going to go even further. Right? Total 9 times as far. That's pretty close to the bottom, probably. So time equals 3. So you get the basic idea. So an object that's just falling straight down would do something like that. It goes faster and faster and faster. Now imagine I took another object. And another object is just moving horizontally at constant speed. Maybe it's rolling across the floor. Right? It has no up-down motion at all. It's just cruising along at constant speed. And let's say after 1 second it makes it to here. This is t equals 1 second. So it starts there. After 2 seconds, it just cruises along at constant speed. Maybe it's here. And you get the idea that it goes the same distance, and there it is at time equals 3, and voila. Well, what happens is if I take a projectile and I launch it at that same speed v, that the marble rolling along would say you track me at horizontally, and I launch it horizontally, it will move at a constant speed horizontally, just like the thing rolling across the floor. Okay, in 1 second, it will also move horizontally to this point. It's just also falling. So it goes from there to there. And a second later, it goes from there to there. And then from there to there. And its path looks more like this. Like that of a parabola. See? So your big picture idea behind all of this, essentially, is that in the vertical direction, which we might call the y direction, so maybe I call up the plus y and right the plus x, since you guys tend to like up opposite in the vertical. What I'm really saying here is that in the vertical direction, your acceleration is 10 down. In other words, g down. You have constant acceleration. Okay? In the horizontal direction, which you might call the x direction, the idea is ax is 0, and therefore your x velocity is constant. Excuse me, not 0, constant. Okay, so if you want to imagine what's happening here, what I'm really claiming is that the motion up, down, and left, right are completely independent of each other. They're completely independent. Okay? How far you move left or right has nothing to do with how fast you're moving up or down. That if I take two things and I launch one horizontally, and I just drop one, they'll always be at exactly the same height at the same moment in time. Does that make sense? The only difference is the one I launch horizontally keeps cruising along at constant speed horizontally as it falls. Does that make sense? Okay? Now, how would I go about solving problems then if this is all true? That I have constant motion horizontally and I have constant acceleration. Why? Well, the answer is the way you're going to go about solving problems is by treating your x's and y's completely separate. That's what you're going to do. You're going to treat these things completely separate. If you want to imagine that you did a little table here of y values and x values, the idea is over here there's only three things that would matter. Your velocity and the x. The sub x means how fast you're moving left or right. Okay? I'll come back to that in a second. This is the time, and this would be your displacement. Here, I'll show you. So let's say that I launch this thing, and by the time it reaches the ground, it's been displaced horizontally by that amount. Some people call this the range. The projectile's range is how far it goes horizontally. The idea is because it's cruising along at a constant rate horizontally, every second it moves at the same rate, this is just calculated as its x velocity times time. The x velocity is how fast, essentially, it's moving this way. So, for example, if Vx is 20 meters per second, it means every second that it's in the air, it would move 20 meters horizontally. So, in other words, if the sun was shining straight down, you can see the shadow moving 20 meters this way. Does that make sense? That's the idea, every second that it's in the air. Now, Vx is not the overall velocity of the object. This is just a piece of the velocity. I'll get to that in just a second. This is just about how fast it's moving left or right. It has nothing to do with the up or down piece. Okay? Now, for the up or down piece, there'll be a velocity as well. And it's the vertical component of the velocity. We call these components. This is the x component, or the horizontal component. And the other piece will be the vertical component, or the y component. And the idea is the y component of the velocity is the velocity you would have that's identical to the free fall. So if I just drop something, okay, it'd be how fast in this direction it's moving up or down. So when I'm right here, for example, the object is actually moving neither this way nor this way, it's going sort of that way. When it's here, it's, you get the idea, it's going like that. Here's going like that, here's going like that. You can just picture this, right? Now, if I were to break this into components, I would say this is a combination of some x velocity and some y velocity. Vx, Vy. And what happens is, every time I look at another spot in this picture, the x component stays exactly the same. But the y piece gets bigger, because after all, you're going faster and faster down, just like free fall. See? And if this side gets bigger, well, that stays the same. Of course, this gets to be steeper. Okay? Here, I'm running out of space, but I would draw the same x, but a much bigger y down, it would be even steeper. You get the idea. Okay? The hypotenuse here is like how fast you're going. It's like your speed. Does that make sense? Like the magnitude would be like the speed. And this angle kind of tells you, which direction you're traveling in, where theta is going to vary. See how this works? We doing good so far? Okay? So this is your Vx and this is your y. When I say your range is Vxt, I mean only this piece. It's the x component of the velocity. The velocity itself is a vector. It has a size and a direction. It's like this. This is like the velocity vector. With a little arrow on top to remind you it's a vector. But I can think about moving this direction as a combination of moving that direction and that direction. Does that make sense? Sort of think about it that way. And so the idea, really big picture behind all of this is the motion up, down, left, right is independent. And to do all of your calculations, you're simply going to break your velocity. Like imagine I launch something not horizontally but at an angle. I'm going to break it into pieces. The x piece and the y piece. Whatever I get as the x piece, the horizontal component, that will never change. As long as it's in the air, it just keeps cruising along at constant speed horizontally. See how this works? What do you suppose happens with the y piece? It varies just like free fall, right? Just like free fall. Constant acceleration down. That's the idea. So you treat the vertical position, vertical motion, identical to free fall, and you treat the horizontal motion as constant motion. I mean, that's the idea, and you combine the two things. So in the x direction, it's really simple. You got three different things. There's one equation type you get together. The only equation you will ever use over here is that the range is Vx times t, and that's it. I mean, there's one equation, we're done. You know, any two of these three, you can get the other thing. Does that make sense? In the y direction, there are, of course, 5 things that might matter if you use the version of the equations I like, which are not the ones on the chart. You've got Vy initial, Vy final, Ay, time, and displacement in the y. And all of this stuff is only about vertical motion. This displacement is not how far you've gone this way, it's just the vertical displacement. It's that piece of it, okay? These Vy initial, Vy final are not how fast you're traveling. They're how fast and which direction you're traveling vertically alone. Only that piece of it. It's referring to only this piece of the motion. Does that make sense? That component of your velocity. Okay? And here, of course, you need 3 of 5, right? If you can get 3 of these 5 things, then you should go grab your equations and go solve. All those equations you've been using, you solve. Just use y's. So, for example, you can use Vy final is Vy initial plus Ayt, right? It's just a constant acceleration equation. Final velocity, initial, and time. So, or you could use displacement in the y. Is Vy initial t plus 1/2 Ayt squared. Or you can use Vy final squared. Is Vy initial squared plus 2 Ay double. They're all the same things you're used to. It's just that I'm only using y pieces in here. Does that make sense? So the critical piece I just want to drive home is so important. This is so important. At no point in any of these equations, this equation of the x, or these equations of the y, will you ever use how fast it's going overall. You'll only use the pieces. Okay?